Recording. Any questions, guys? How are you all doing?
Doing good.
Doing all right.
Yeah, let me throw you guys over there. We don't need to do this. So let us go to where we left off before. And we can go through this really quickly. Go to page 77, if you would, please. Okay, and they talk about if you look at the concept of an air parcel, that's where I came up with calling it a Vegas box. Dry adiabatic lapse rate, we've already derived that, which is 9.8 degrees Celsius per kilometer. And really, I would say in the future, if you're doing problems, that's the value you should have, not 10. You turn the page. I hope you work through the Poisson's equation derivation. Are there any questions on any of the steps that are in there? Any problems with any of the steps in there? Okay. Hold on. Then we go to the thermodynamic diagram, and we talked about the two different types, the Stufe and the log P. So you just take the logarithm, which will skew the temperature. It's interesting. If you take a look, last paragraph on page 79 before 3.5, suggests that ambient air brought into the cabin of a jet aircraft at cruise altitude has to be cooled by about 20 degrees Celsius to provide a comfortable environment. So when they pressurize the camera, it's actually a cooling system, not a warming system. Is that why it's always so warm in the airplane, Mike?
No, we have they're called PACs, pneumatic air conditioning that regulate the temperature. It's really hot because it's compressed in the engine itself. So we have to cool it off. It's a cycle of it, expanding the air and throwing in water to cool it off. So
yeah.
It's a system to keep it moderate.
Okay.
So if you're hot, your pilot's just bad.
Okay, water vapor in the air, turn the page. We have already talked about this. I think we've already done this one, right? We have mixing ratio. We have specific humidity, which is Q, right? And that's important that you remember that. Remember the difference is mixing ratio is the mass of vapor divided by the mass of the remaining dry air. So it's the ratio. Specific humidity is the mass of the vapor compared to the mass of the entire parcel of air. So they're not exactly the same, but they're close. And would you also agree that they are conservative in a parcel's motion? And I think this is a concept you need to get into your mind right away, is when I say it's conservative, meaning if you follow a parcel, the change in W is always going to be 0. The only way that W changes is if you have evaporation or condensation. Okay? Now, saturation vapor pressure. Let's kind of read through this, because Mike, we were just talking about it. And the thing that I want to make sure you get on here is, and we have discussed this before, so it's not completely new. Let me go over here, get my pen out. We'll go, oh, that's good. Okay, and so we go with E. What does E stand for?
Partial pressure of water vapor.
Right, it's the partial pressure of water vapor, super important. So do you agree that E is, in all accounts, a measure of the amount? But instead of mass, it's going to be pressure. Well, E sub S is saturation vapor pressure, which is a measure of what?
Saturated.
Well, what I'd like you to do is think about the measure of capacity. It's the saturation vapor pressure. In other words, if the air were saturated, what would it be? Now, if you take a look at figure 3.8, which is, you know, I used to not teach this, and now I'm kind of teaching it more and more. Imagine that I have a box with water in the box, okay? So that's water. I do not need to have air, just so you know. I don't need to have air in the box. In this scenario, some of the water is going to come out of solution, out of the liquid, and evaporate. Soon as that happens, we now start to get vapor in the box. So if it was in a vacuum, it is no longer in a vacuum. Okay? Now, as these molecules are flying around, some of them will come in contact with the water and recondense. Okay? So saturation in actuality is the rate of evaporation is equal to the rate of condensation. That is what saturation is. Now I want to imagine that I heat this entire system. When I heat the entire system, what am I actually doing?
You're increasing the rate of evaporation.
Well, yeah, but no. I would think of it more in terms of at the molecular level.
Energy, work.
If I heat it, what am I increasing?
Molecular motion.
Right. It's right. I'm increasing the kinetic energy, which is the average kinetic energy is the temperature of the molecules. So the molecules are moving faster. As they move faster, more of them will want to be in vapor. So what I say is I'm going to have more vapor. More vapor will be in the air. And now, Jim, when you talk about it, right, you are increasing the evaporation because you're giving each molecule more energy to leave the liquid state to go into the vapor state. But since there's more vapor in the air at this point, I'm also going to increase the rates of condensation because the molecules are moving more and will hit the water more frequently. As a result, when I reach saturation, I will have more vapor than I did at a cooler temperature. So there's a relationship between vapor pressure and temperature. Now, if I drew off a graph, I want to put temperature on this axis. Why is that? Temperature on the horizontal axis because it's the independent variable. And so what does my graph become? It's going to be an exponential graph. So now,
Saturation implies equilibrium between the two,
between evaporation and condensation, correct.
no matter what the temperature.
No matter what the temperature is.
Okay.
So what that really, you see, Jim, if you think about E sub S as being a, like an if term, how much would be in the air if the air were saturated? So we're assuming the air is now saturated. There is some amount of vapor in the air. That's E. If I warmed it up and then the air were still saturated, I would now have more vapor. So E sub S is how much vapor would be in there if the air were saturated. Who would like to read? Bruce, would you read for me section B on page 80?
Section B on page 80. Oh, the whole thing?
Yes, please.
Consider a small closed box, the floor of which, I have to move a microphone, wait a minute.
Oh, you're good.
Consider a small closed box, the floor of which is covered with pure water at temperature T. Initially assume that the air is completely dry. Water will begin to evaporate, and as it does, the number of water molecules in the box, and therefore the water vapor pressure, will increase. As the water vapor pressure increases, so will the rate at which the water molecules condense from the vapor phase back into the liquid phase. If the rate of condensation is less than the rate of evaporation, the box is said to be unsaturated at temperature T. When the water vapor pressure in the box increases to the point that the rate of condensation is equal to the rate of evaporation, the air is said to be saturated with respect to a plane surface of pure water at temperature T, and the pressure E sub S that is then exerted by the water vapor is called the saturation vapor pressure over a plane surface of pure water at temperature T.
Okay, so when we define relative humidity as being E over E sub S, well, hold on a second. Let me think this. We are defining relative humidity to be W over W sub S. That is approximately equal to E over E sub S. These are not exactly the same, and I think that there is a place in the book, yes, that will talk about what that is. Okay, so we're going to be getting to that. So the point is, this is almost the same. So saturation is when these are the same, just like saturation is when these are the same. But all of this is based with respect to a plane of water, right? So this is a puddle of water on the bottom of this box. It's a plane. In the atmosphere, when we have small drops, this does not work. In some of my classes, if you've taken it, we talk about that there is a measure of entropy or randomness, that getting to that sphere is not good, so it actually requires more. It's the large surface that matters. So even Mike, when you're talking about an airplane, right, the small droplets stay as liquid, but as you go through a cloud, you start to coat the wing with water, the droplets become bigger, and the freezing point gets smaller, or gets warmer, I guess. So rather than -10, where it's still liquid in the cloud, when it covers the wing, those larger droplets are now freezing at like -2. So that's where icing comes into play. So as long as the drops are small, you're not going to have a problem. It's when you get larger drops or a plane of water and then freezing, it's at 0 degrees Celsius for the plane. Okay. And we talk about this meaning it's an extremely high ordered crystal. The molecules have to have a certain arrangement. But once you start that arrangement, all the other molecules can line up and ice can grow really rapidly in a plane. You've seen, anytime if you've seen water on your window or your windshield, it starts in a little area and it can freeze very rapidly as it spreads. So you think of an ice crystal as growing, and it grows rapidly because once you give it an arrangement, it's easy to follow suit. So you have to give it that. But in any case, what they're saying here on this next paragraph is, well, what if instead of water, what if we replace this with ice? Okay. What that does here, go ahead and would you read that paragraph, Jim, similarly?
Similarly, if the water in figure 3.8 were replaced by a plane of pure ice at temperature T and the rate of condensation of water vapor were equal to the rate of evaporation of the ice, the pressure E sub SI exerted by the water vapor would be the saturation vapor pressure over a plane of pure ice at T. Because at any given temperature, the rate of evaporation from ice is less than from water, E sub S of T is greater than E sub SI of T.
Now, if I were writing this book, I wouldn't write that, because if I'm going from ice to vapor, what is that process called?
That's a phase
Deposition.
change.
Ice to vapor is what?
Deposition.
No.
Sublimation.
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 I knew it was
And
one of
then-
the two.
And then the opposite would be deposition. And that should make sense that given at a certain temperature, less, like the vapor going from the crystal to the air will have to have much greater temperatures in order to get that to happen, which means I will not have as much vapor in the air when it's with respect to ice when the air is saturated. So it's more difficult to go back and forth with greater amounts of heat required to go
Because
back.
you're going through, in effect, two phase changes.
Yeah, and it's actually skipping through the phase change, but you're just
Right. Because
Right.
ice has a triple point near freezing.
So when we start talking about words, we start using terms of latent heat. The heat required for a phase change. Now, hold your page there and go to the back of your book to the appendix for the units. And I want you to go to water substance, page 467. And what we're going to do is we're going to say, actually, turn the page, 468 top. Latent heat of vaporization. So how much heat is required to vaporize water at 0 degrees Celsius?
2.5 times 10 to the 6 joules per kilogram.
Okay, so 2.5 million joules to vaporize a kilogram of water. Now, how much does it take to fuse it? Fusion is the heat required to go from ice to liquid or back and forth. That's called fusion. So how much heat is that going to be?
About a magnitude less.
Right? 3.34 times 10 to the fifth. That is like an order of magnitude less, a power of 10 less. So it's much easier to melt ice into water than it is to go from water to vapor in terms of how much heat is needed. Now, here's the question though. How much do I need to sublimate water? And the answer is 2.85 times 10 to the sixth. So it takes more energy to do that, to sublimate water, and that's to go without the middleman, to go straight from ice to vapor or vapor to ice, which some areas, vapor to ice could be considered sublimation. That's why they call it the latent heat of sublimation, but we will call it deposition from here on out. Okay, so it does take more of that. It also takes less latent heat to vaporize water when it's already at 100 degrees Celsius. So 2.25, which tells you that you're taking about 2.5 times 10 to the fifth joules per kilogram to raise the temperature of water, which is going to be a result of what specific heat would be, something along that, if you go back to the page before. It's a little bit different, but you get the idea.
All right.
So as a result, and this is important, is E sub S of liquid is greater than E sub S of ice. And the way that the book does this is they'll go ESI if they mean ice. But that's basically what we're saying. Okay, and so what they do is they show you this graph on figure 3.9. Do you think that might be important that you understand this graph on 3.9? First of all, before I erase this, is there any question on this?
So effectively what we have is that the most important thing is that it just takes more latent heat to phase shift ice than liquid.
Right, and as a result, given a certain temperature, you don't have as much available to do that. So you're not going to put as much vapor into the air when it is saturated. And as a result, the amount of vapor over ice capacity, how much could be there, is going to be less than that over liquid water.
Gotcha.
Got a question about what I read.
Okay.
It's about water evaporating and the number of water molecules in the box increasing.
The number of vapor molecules.
Okay, it just says water in the book, but
Yeah. You're not changing the amount of water because you're just going from liquid to vapor.
got
So
it.
your mixing ratio would go up.
You have less water, you have less liquid molecules and more vapor molecules.
Correct. So the total number, actual number of water vapor molecules would be the same.
Dang.
I don't know if this will work. It probably will. Yeah, let's go here. Okay. Let's go back for a second. Why don't we just use it here? So let's look at this graph here. And I'm saying at this point here, that's the maximum difference between those two. Now remember that ice crystals in a parcel of air grow at the expense of supercooled water, which evaporates. That's the key of what process. What is that process called?
Geron?
The Bergeron process, or if you want to be, I think that's how you spell it, might be IE, Bergeron-Findeisen process. So between -12 and -16 or 18, I think it's usually -16. -12, that's known as the DGZ. Now, in any case, the way I look at it is that anywhere between around -20 to -10, you have a pretty substantial amount of difference. The greater the difference, the more vapor is going to come out of the air in that process. Okay? But what I'd like to do is I'd like to look at this. Nope. Let's look at saturation vapor pressure versus temperature. And I want to look at a good chart for this because there's something kind of important about this. Do you see? Does the book have one that goes up to 100 degrees Celsius?
No.
No, that's way too hot. This one kind of does. There. Well, let's go ahead and look at this. Now, there's something important. So ready to write this down? The temperature for which water boils is equal to the saturation vapor pressure at that temperature.
Okay, so that's what you drew. Okay.
right? That's kind of what this is.
What does the graph look like for ice?
It would be the same thing, just underneath it. So, I mean, you could kind of, if you took figure 3.9 and you did that. So I don't know, let's go
'Cause
saturation, vapor, pressure versus ice. It's not that different.
Oh, that's interesting. But yet you end up with a blue.
It's just a little bit, and there's your temperatures, because obviously above 0, it's not. So you're really looking at somewhere around 263, 261 is where your difference is the greatest. So it's not that big of a difference, but it's certainly enough to make things work. And so when you graph those differences out and expand the axis a little bit, that's the axis that's the graph that you get. So it's kind of cool. It just it's more pronounced, but you're really kind of looking on this graph is you're not looking at a whole lot of difference, just a little bit. But going back to the water vapor or water boiling, and we go back in our diagrams to this diagram, for instance. Oops, where was it? Well, something like this, right? Then the question is, all right, at 100 degrees Celsius, what is the saturation vapor pressure here? And what's the answer?
About 1,000 mil.
Sea level.
1,013.25 millibars.
Sea level pressure.
See, well, remember that's standard sea level pressure. When I say standard, what I'm saying is a standard atmosphere. So in a standard atmosphere at 1,013.25 millibars, then we fix the boiling point of water at 100 degrees Celsius, because that's where it fits in there. So it makes a lot of sense to call that a standard atmosphere where water boils at 100 degrees Celsius. Because the boiling temperature of water, we always say 100 C, but that's not really true. It varies depending on the vapor pressure on this chart. So if I drop it down to 850 millibars, let's say, so here's 850 millibars, like in Denver, what temperature will water boil at? You know, 92 degrees Celsius, maybe 18, maybe 190 degrees. That's still pretty hot. But if I were up in some of the high terrain of the world at 700 millibars, now we're dropping down to under 90 degrees Celsius, and we're actually losing a fairly substantial amount of heat. The water boils at 700 millibars at a much lower temperature. Okay, so what if it was at 0 degrees Celsius? Now you can't read this here, but do you agree that water would boil at 0 degrees Celsius at very low pressures? The answer, E sub S at 0 Celsius is 6.11 millibars. Now, what does that tell you?
The lower the pressure, the less heat you need, or the less capacity the air has for holding
Well,
water vapor.
Yeah, but when you're super cold, I mean, super high in the atmosphere, can liquid water exist?
No.
Because it would boil away. When I was a kid, I took a glass Coke bottle, filled it with very warm water, and I left just a little space up on top, and then I would suck out as much air as I could, and I could actually bring bubbles up. That sort of boiling. So this is something you should all dry out sometime. Take a beer bottle or something, fill it near to the top, and then use your mouth to suck out as much air as you can to create that vacuum, and you will see bubbles coming up in the bottle because you're boiling water. But it also says, if E sub S of ice is very close, are you really going to even get ice at really high altitudes?
No.
All the water will exist in vapor form because even the ice would sublimate. So we don't go real high in the atmosphere and see clouds. And it also gives you an idea, like if you were to bleed in the thermosphere, what would all the blood do? If you bled out, it would. I mean, they always show you in the movies that it turns to bubbles, but what it really would do is it would evaporate.
Are there movies that do that?
Yeah, there's Star Trek used to have one where they were in zero pressure, and the blood, there were just balls flying around. That's probably not what would happen. I don't know what the vapor pressure of blood is, but I'm assuming it would want to go to vapor. Okay, so that's kind of interesting, don't you think?
Mm-hmm.
So I just wanted you to know that. Now, the last thing I want to talk about is latent heat. Why is it that when I've got water, oops, if I've got water in a box, and underneath that box, I've got flame, so I'm heating the box, making it warmer. Why is it that as vapor starts to continuously liquid continues to evaporate, why does this stay at constant temperature? Why is it at constant temperature?
The liquid is constant?
Yeah, I mean, let's say it's a 1,013.25 millibars of pressure. Okay, that's the pressure. So we know that the temperature of the water goes to 100 degrees Celsius. Why, when you're adding heat, does it not get warmer?
Because of the phase change being initiated by the heat from liquid to vapor.
But why doesn't it still get warmer? Can't it do both? I mean, what's happening is when a molecule goes from liquid to vapor, it's going into a higher state of energy.
Right.
And what's another way to say that? It's a higher what?
Higher kinetic energy?
Well, that's true, but there's something else. There's another word.
Phase?
Oh, entropy.
It's a higher entropy. And this is important when we get into the second law, or the first law. We want to get into entropy in a little bit more detail because it is going to play a role. We're going to use an entropic version of the first law. By the way, what is the measure of entropy? What's the symbol?
H.
No, that's enthalpy.
Enthalpy.
Theta E?
Not theta E, just theta.
Just theta.
That's why a line of constant potential temperature is called an isentrope. Isoentropy. So theta is entropy. So we are going, in this scenario, higher entropy. The temperature is staying constant. Now I want you to think about this. Imagine that I had a room full of people and I said, every time you got $100, you leave the room. So let's say to start, everybody averages $90. Some people may have $96, some people may have $84, whatever, but you're averaging $90. and I'm just going to be dropping dollar bills into the room, and you collect them. Now, all of a sudden, at $100, you're like, I'm leaving the room. So when this leaves the room and goes to vapor, and you're leaving the room with dollar, what happens to the average temperature left behind? What happens to the average amount of money that's left behind when the person with the most money leaves the room?
It goes down.
So I keep giving it more and more money so that I'm keeping that average the same. But every time somebody leaves, the average would want to come down. That's why I can continue to provide energy and not see the temperature go up, because they keep leaving. Does that make sense?
Because that's why when you have like a bigger pot of water, it takes longer to boil.
Yeah, but the key question here, James, is that why is the water always at a constant temperature? Water boils at a constant temperature. Why is that? Because I'm adding heat not to make the average go up, but I'm adding heat to make the average stay the same, because I'm losing molecules with more energy to vapor. Now, eventually, if I were to take a closed container and put more and more vapor in here, more and more and more and more and more and more, do you agree that would increase the pressure? So what would happen to the temperature of the water when it boils? Did you understand what I asked? I'm heating the water more and more, and I'm keeping it as a closed container. More and more vapor is going into the air, which does what to the vapor pressure?
Increases it.
Which means the outside pressure is going to be more. So what happens to the temperature of the water boiling? Remember, we said it's the
Imagine it goes
vapor,
up.
the temperature at which water boils is determined by the saturation vapor pressure at that temperature. So because I have more water vapor in the air and I'm increasing the pressure, the temperature can go up. This is what a pressure cooker does. A pressure cooker keeps the pressure very high because I never let anything escape. And as the pressure is high, the water temperature goes much hotter before it turns to vapor. This is what your coolant, your radiator does of your car. You're under high pressure, it gets really, really hot, and it stays as liquid because it's under high pressure. So what if I put a hole in the side of the container, like a hole in my radiator? What happens is all of that air wants to come out, the pressure drops, and all that liquid turns into vapor. But what's the temperature of that vapor? It was the temperature of the liquid, which is much higher because it was under high pressure. So if you were to release the radiator cap, all of that, you get what we call a vapor burn. It's really all the liquids turning into vapor, super hot temperatures. Water has an extremely high heat capacity, so you're going to have a huge amount of heating going on. Now, true, some of it will turn into steam because it recondenses. Steam is technically not vapor, but whatever. You have a bunch of hot water on your face, which has a really high specific heat, a really high heat capacity, much more than air would. So you put your face into an oven at 500 degrees and you're like, oh, this is hot. You put your face into water vapor at 500 degrees, you go burn your face off. Water has a much higher heat capacity.
So this is pretty much why that when you like take the lid off of a closed environment, there's always a huge burst of heat in the immediate vicinity.
Yep, you're expanding the air. Now expanding air cools, so there is some compensation for that. But the vapor turns back into liquid as the pressure drops or as your temperature cools. Anyway, we can go past that. Let's go to the next page, page 82. I just thought we should talk a little bit about water and how that all works. Okay, so now the next thing is, well, we know the mixing ratio is at saturation is equal to, or actually is defined as, the mass of the vapor at saturation divided by the mass of the dry air. Now it says, because water vapor and dry air both obey the ideal gas law, what they're doing is they're saying, all right, they're in the same volume. Do you agree with that? So I can divide the numerator by volume, divide the numerator by volume, and then I get the density and what does this little prime mean? What's the prime? What do we call that?
The partial.
The partial density. So you're saying, what would the density, right? Because what you have here is you have a box. It's the same volume. It's full of vapor, right? Blue for vapor. And it's full of dry air as well. And there should be a whole lot more dry air than vapor. Okay? So you're saying in this volume, if I'm looking at only the mass of the vapor, when it's saturated, that will be the partial density, the density that water vapor would have if it alone contributed, were alone in the box. And the same thing is true with the mass of dry air. But the ideal gas law, which is, again, you want to think P equals rho RT. So I'm solving for density. So density is going to be the pressure divided by RT. So what that will become for us is the, well, what would the top be? It wouldn't be, pressure. It would be what? It wouldn't be P. What would it be?
Saturation vapor pressure.
Right? And it's only saturation vapor pressure because the air is saturated. So E and E sub S are the same. So the pressure of the vapor is E, but we also know that's E sub S divided by, what would it be on the bottom? Not the bottom here, but remember this.
P minus E sub S?
It would be RV, right? The ideal gas constant for vapor times the temperature. What would the denominator be? Look what they put in there. It's the total air pressure minus the contribution of vapor divided by RD times T. Now, what can I get rid of right off the bat?
The T's.
The T's, right? Now, why is this? What is this supposed to? Why is pressure equal the pressure of the dry air equal to the total pressure minus E? What tells us I can do that?
Is that Dalton's law, partial pressures?
That's the answer I was looking for. Dalton's law. That the total air pressure is equal to the sum of the dry air plus the vapor pressure. It's all, I can add the constituents. So this is Dalton's law. That's what goes in here. Okay, now that I have that, I realize that on the right side of the equation, I have RD, if I invert, over RV, right? Because this is in the denominator, that's in the denominator, I can
Right.
invert, times E sub S over P minus E sub S. But what is RD over RV? 0.622 E sub S over P minus E sub S. So what I'm doing is I'm creating in here a relationship between W sub S and E sub S. That's what I've got. I'm trying to say, how are they similar? And they're close, but they're not exact. Okay, now what? Now what's their next step? You go look at the next step. I'm going to fill my coffee unless you need to fill your coffee.
Yeah, okay.
Did you get it?
Yeah,
This is that algebraic manipulation that you will see a lot of times.
it's not
Wallace
algebra.
Hobbes' trick of tiny numbers.
It's a trick of tiny numbers,
It's abstract algebra.
right? This is just a tool that you will see quite often. So hold on a second. So what's it going to be? I'm just trying to get my stand minutes. I was too quick in getting the coffee. Okay, so what that means is x divided by y minus x is approximately equal to x over y if x is much smaller than y.
Or vice versa.
Now, why do I allow that to happen? So in other words, let's just try that. Let's go 2 divided by 100 minus 2. So on your calculator, 2 divided by 100 is 0.02. What's 2 divided by 98?
Work.
What's 2 divided by 98?
49.
2 divided by 98, flip 49,
1 over 49.
which is how much?
10204.
How much?
2.04 times
204.
10 to the minus second.
Okay, that's pretty close.
Yeah.
You're off by 4,000. It's a small amount. So what's our values of E sub S? Well, E sub S in the atmosphere when we're dealing with it, right? Because we're only dealing with temperatures up to how much? Well, here, let's take a look. Even at 40 degrees, E sub S is less than, maybe 90 millibars. So it's going to be off by a little bit at But that's at 104 degrees, right? Because that's a bigger number. Okay, so that gets me to getting rid of this. And now we go W sub S is approximately equal to 0.622 times E sub S over the pressure. So I don't, you want to try something? You want to be daring? Say yes, Paul.
Let's go.
Because I'm going to try something that I have no idea whether I'm going to do this correctly at this moment in time.
Whoa.
So the reason we're getting rid of E sub S on the bottom is because it is so tiny that it's effectively the same thing.
Yes, this is only true when this is much smaller than the thing you're subtracting it from. Okay, so what we want to try to do is, okay, well, RH is W over W sub S. Convert that into E over E sub S. So how does W convert to E? How does W convert to E?
E is equal to W, well, taking 359 and solving.
Right? If you did that, what would that formula be?
Ugh.
Well, so this is 3.59. It's just algebra, right? E equals W over W plus epsilon times the pressure.
Right.
So I need to go, this is WE plus epsilon E equals W times P.
Right.
Now I have epsilon E equals W times P minus WE.
And then divide out. Yeah.
So that would be epsilon E
Over
divided by P
minus
minus E
is equal to W. Right.
So over on the top, what does that become? Epsilon E divided by P minus E. What's the bottom? 0.622 E sub S all over P. Okay, so that is what relative humidity is. Now let's simplify this. How are we going to simplify this?
Bring P up to the top.
Okay, so let's go step by step. I'm going to put, well, what's epsilon? 0.622, isn't it?
Right.
So don't I have that in the numerator and the denominator?
Cancel it.
So I can get rid of epsilon. Now it looks a little bit more doable. Get rid of that stupid thing. And I've got pressure times epsilon pressure times E over P minus E divided by
E to the S.
the S. Okay, so what I really want to do is I want to go E over E sub S times P over P minus E. Now, do you agree that this is almost equal to P, and then the P's we cancel?
Right.
But it's not exactly, is it?
So it's an approximation.
So W over W sub S is almost equal to E over E sub S. It's just not exact. Because in here, this difference is something, but it's small. It's like close. It's not exact, but it's close.
Will the graphs of the two be the same or similar?
E sub S and W sub S, yes.
So it's a good approximation through the
It's a
entire
good approximation.
through the domain.
And it's going to be exponential. It'll just be, you know, like the E sub S of
Okay.
ice and water, which is
So it's basically going to be shifted.
Yep, just a little bit. But at least you see that these two things are approximately equal to each other. They're off by the difference in this.
So the big
That's where the difference comes from.
So the difference is over pressure minus capacity.
Minus whatever the vapor pressure is.
Whatever the vapor pressure is.
Pressure minus vapor pressure is the only difference.
So as much as this little trick that we talked about in the denominator is close, that's how close these two things are to each other. They're not exact, but they're close. And I thought that was worth doing. Okay, so and we know that W sub S changes with respect to temperature, just like E sub S changes with respect to temperature. Then over here, look on page 364, the relative humidity is defined as W over W sub S. It's approximately equal to E over E sub S. If you look at equation 365, that gives me the idea of what do I need on a thermodynamic diagram. I need to be given pressure, temperature, and dew point, because the pressure and the temperature give me W sub S on that chart. Given the pressure and the dew point, that gives me W. So that's what it says in 365. A simple rule of converting RH to a dew point depression for air that's greater than 150% is that the dew point decreases by 1 degree Celsius for every 5% decrease in RH. That's interesting. I didn't know that. So if the dew point depression is 3 degrees, the relative humidity is about 85%. And then the frost point's the same thing as dew point. And then they give you a little real simple exercise, which we should know how to do that. Nick, would you read on page 83 after the black square at the Earth's surface?
Looks like a blue square to me.
Or is it blue?
Oh, yeah, I see what you mean.
First column, second pair.
Yep. At the Earth's surface, the pressure typically varies by only a few percent from place to place and from time to time. Therefore, the dew point is a good indicator of the moisture content of the air. In warm, humid air, the dew point is also a convenient indicator of the level of human discomfort. For example, most people begin to feel uncomfortable when the dew point rises above 20 degrees Celsius.
Which is 68. Go ahead.
Oh, sorry. and air with a dew point above 22 degrees Celsius is generally regarded as extremely humid or sticky. Fortunately, dew points much above this temperature are rarely observed even in the tropics. In contrast to the dew point, relative humidity depends as much upon the temperature of the air as upon its moisture content. On a sunny day, the relative humidity may drop by as much as 50% from morning to afternoon, just because of the rise in air temperature. Neither is relative humidity a good indicator of the level of human discomfort.
Yeah, okay, so we can stop there. That's exactly what we talked about.
Mm-hmm.
Okay, then they talk about the LCL, and they talk about the wet bulb temperature. So you can read that on your own. Go ahead to the next page. Key things here. First of all, is the temperature of the dew point is less than or equal to the wet bulb temperature, is less than or equal to temperature. Do they have Norman's rule? Where's Norman's rule? Oh, here, it's the next page.
356.
Yeah, so I knew they had that in there. So let's just take a look at Norman's rule real quick.
Why do they refer to the skew-T LNP chart and not just skew-T?
Skew-T log P,
Yeah,
because that's what a skew-T is. When you say skew-T, it's skew-T log P.
it's implying, okay, it implies, okay.
Right.
I thought there was something fancy, there was something special when they explicitly said log P.
Yeah, no, it's that is what a skew-T is. That's just its thing. Okay, so what I have here is I have a temperature. Here's a temperature. Here's a dew point. Okay, and then to find the LCL, what do? I take a mixing, I'll use the Stuva diagram. I go a mixing ratio constant, which is decreasing at a rate of 2 degrees Celsius per kilometer. I take the temperature line and I go up dry adiabat. That's the LCL, right? We know that. The point is, if I follow a wet adiabat down to the surface, then this point becomes what? What is, oops, not exactly where I wanted it. What does that point become?
Dew point temperature?
Nope.
No.
This is the wet bulb.
Oh, wet bulb.
This is the dew point, and this is the temperature. So keep in mind, dry adiabat from the temperature, mixing ratio line from the dew point, wet adiabat from the wet bulb temperature, and those intersect at the LCL. That's Norman's rule. Okay. By the way, going on, I am not going to discuss this with you on page 86 and 87. I'm expecting that, or starting at Norman's rule, I'm expecting you to be able to read that and get it. This is stuff that we've done in other classes. We do this in meso quite a bit. If we do this in severe, we do a lot of this stuff. So I'm not going to go through it again with you in this class. Now let's go to latent heat. So page 84. Any question on Norman's rule? Probably never heard of that, but it's important. So when we were on a storm chase and I take a sling psychrometer, I measure the wet bulb. And so by measuring the wet bulb, I can calculate the dew point. So I usually, when I'm on a storm chase, I'm doing this, not dew point. I figure out the dew point. Okay, now, latent heat. In this case, the increase in internal energy is associated entirely with a change in molecular configurations in the presence of intermolecular forces rather than an increase in the kinetic energy of the molecules. So that's what we talked about. The temperature remains constant until all of the ice is melted, for the same reason that I talked about with the money in the room. And then they give you the terms, which we went through in the book. As will be shown in sections 3.7.3, the melting point and boiling point of the material depends on pressure. When air pressure, and then they talk about saturated adiabatic process, talk about latent heat release, and everybody knows that that's the case, right? So do you remember, I do this because I think this is one of the most vital things that we do in our classes at the introductory level, is we will say that the wet adiabatic lapse rate is equal to the dry adiabatic lapse rate minus the amount of latent heat that is released. And that depends upon how much water vapor condenses, which is a change in the mixing ratio, which depends upon how much the saturation mixing ratio changes, which is dependent upon the change in temperature and the temperature. Now, I'm assuming all of you, tell me if I'm wrong, I'm assuming that all of you have your notes from either intro or severe weather where we do this very thing. Nick, did you take this? Did you take intro or severe with me?
I took it intro with Ron.
Did you do this phrase right here?
I can't remember for sure, but I've got my notes here. I can look at it real quick.
Bruce, do you have that in your notes? I'm assuming you keep your notes, right?
Yeah, I've got it there in the cabinet behind me.
Jacob, you have yours, I'm assuming, James.
Yep.
So just take a look at this. I will go through really quickly. Basically, it's this. So because you guys are more advanced, I don't want to spend a lot of time. We said that the saturation mixing ratio increases exponentially with this. So we said, hey, the change in the amount, this is delta T, and that corresponds with a change in W sub S. The yellow delta T corresponds with that. If I were to do it in pink, and I were to do this same thing, I would say, all right, given that same change in temperature at higher temperatures, that's going to be a much larger delta W sub S for the same delta T. So this is the same. We're saying that the change in the capacity is a function both of the temperature change, delta T, and the temperature where that change takes place. The change in the capacity, since the RH is we're talking about in saturation, these two are equal. So that's why this is the amount of vapor that actually comes out of the air. The more vapor that comes out of the air, the more latent heat. The more latent heat, the slower the wet adiabatic lapse rate. But this is saying this is a degree Celsius per kilometer. This is an amount of latent heat. And do you understand I need to know how much latent heat is released in that kilometer, how much water vapor comes out in that kilometer. And since it's exponential, I'm going to have to do something a little bit more funky because it's nonlinear. So that's what this entire derivation that's coming up is going to do.
So WS1 is less than WS2, delta S2.
Yes, this is more.
Right.
So the corresponding change in the capacity is more when the temperatures are warmer. So that is stuff that we go through. I do that in both my intro class and my severe weather class because that is the key to being able to do this. Just so you know how my brain works, I teach intermediate and I go, okay, what do I have to teach in my intro level classes so that you see it again in a better way in intermediate? So now we go, all right, let's take a look at this. So can I erase this? You should have that if you, and then please go find the notes on that. I think that's something that's important to have. Now, we are looking for, it says substituting 3.3. So what's the first thing we need to do? What is 3.3? Now I'm going to guess, what do you think that is 3.3 is?
3.3.
Ideal gas law?
P alpha equals RT. And then the other one is 3.46. What do you think that is? It is going to be, what is that?
First law of thermodynamics.
Right? Cp dt minus alpha dp. I'm using this form. There's a reason for it. But this is kind of like somebody a long time ago figured out if I did this and manipulated it. And your job at this point is say, all right, what am I doing? I'm taking the ideal gas law and I'm taking the first law of thermodynamics. So I'm going to go dq dt. So I'm dividing through by dt. Or, sorry, I lied. I'm dividing through by temperature is equal to Cp dt over T minus, now I want to keep dP in there, but I want to get rid of alpha. So it's going to be RT, right? Listen, watch. This is going to be RT times dP over P. But because I'm dividing through by T, I get rid of the T.
So it's R over pressure. Right.
Now, why do you think I want to do it this way?
It's R.
Why do you think?
Because CP doesn't depend on T and R doesn't depend on T, so you can get that out of the integration.
Well, no, but I mean, what's the reason of setting it up into this format? What do I like? I like to have logarithms.
Oh, okay.
Right? Because I know when I integrate it, this is an integratable, both of these terms are integratable. Now, it says from 3.54, so let's go back to 3.54. What's 3.54?
Theta, Poisson's equation.
Okay, so we know that theta is equal to T over P naught over P to the R over CP. Now, what did they do? That's not what's written there. So what did they do on here? Like, where did they get that line? It says from 3.54. What did they do?
They integrated.
No.
Oh, no, they got raised it to the E? No.
I just took the natural log of both sides.
Yeah, natural log.
So guys, everybody look at the screen.
Yeah.
So what you want to be saying in your notes as you're really doing this is you want to go more than just what I've written. You want to say ideal gas law, first law of thermodynamics, the depth Poisson's equation, and then you take the logarithm of both sides. Well, the left side's easy. What's the logarithm of this side? Well, the first one is I can take the logarithm of t plus the logarithm of p naught over p to the r over cp. But what's another thing I can do to simplify this?
Move the R over CP out to the front.
But what else can I do now?
You can say log P0 minus log P.
Right? These are all just rules. Now, I want you to see something here. This is the natural log of a number that we are assigning, P naught, let's say 1,000 millibars. So do you agree that this is actually a constant?
Mm-hmm.
Minus the natural log of P. And that, all I'm saying then is natural log of theta is natural log of T minus the natural log of the pressure plus a constant.
Okay, hold on.
And
What happened to the R over CP?
R over CP.
Yeah.
So minus R over CP.
Oh, hold on. I gotta move my thing again. You have a really, really good habit of managing to keep writing exactly where my face cam lists is.
Yeah, that's why I've got two monitors, because I look over here and it might be different, but at least I can not have to write over faces.
Okay, hold on.
You know, it's funny, it takes a while to convert from teaching in a classroom to teaching online. But I'm telling you,
In your
I don't know
final,
about you, given the fact that I know all of you, that you're good students, except for Jacob, and
Hey.
hey, well, that's because your face is not here, and you're more advanced. This is actually working out. I kind of like teaching intermediate on virtual. I would like to be in class, but there's something nice about this, I will say.
Can you repeat the second to the bottom line? I can't read the last
Okay, so let me
part
do
of
this.
that there.
I can easily redraw that.
and in your final equation, you probably want, you want a
Yeah.
minus there. No, wait a minute. Yeah.
Right. I mean, that's exactly what it is in the book. Then they go, okay, wait a second. Let's differentiate this. Let's take the derivative of both sides. Do you agree that's a legal move? So what is the derivative of the left side? So we're going to go up here. And we're going to go, what's the derivative of the natural log?
1 over theta.
Well, d theta
Oh,
over
okay.
theta. And then what's the derivative would be dt over t. And then minus r over cp's are constant. And the derivative of the natural log is dp over p. And what's the derivative of a constant?
0.
0.
So it disappears.
So they disappear. And then what they did is they multiplied through by CP. So watch this. I'm going to do it here. Okay, watch. I'm going to get rid of it there. And I'm going to add it. And do you now agree that I've got this equation as the same? Except for what? What's different between these two equations? Do you agree that, here, watch this.
Wait a minute.
The right-hand side and the right-hand side are the same,
Right.
which means what? It means
dq over t, you can substitute dq over t
over
for that.
t is equal to Cp d theta over theta. Okay, what do you think? So far, so good? Are you following it step by step?
Yeah.
Mm-hmm.
Anything that you can't follow?
When you have the constant for the last part where it's still a logarithm, that's what CP is for this, right?
Well, this constant here, if you want to think about it, James, is just R over Cp times the natural log of P naught.
Wait a minute.
But
Okay.
P naught is a given number. It's a constant. It's not variable. It's 1,000 millibars. R and Cp are the same. So this whole thing is just a constant. And when I take the derivative of a constant, it goes away.
Okay, so it effectively just
But this should
deletes
make
itself.
sense to you. Do you agree that when I take dq is an infinite amount of heating at a temperature? And what will that cause? It will cause some change in the potential temperature at a potential temperature.
All right.
So if I give some amount of heat, and let's just think about this. If I release some, or if I give some amount of heat at, let's say, 20 degrees Celsius, that will cause a change in the potential temperature depending on the theta. But let's say we're at 1,000 millibars. So the heating changes the potential temperature, which should make sense because potential temperature is a measure of heat. It's a measure of entropy. So I add more heat, I have more entropy. Duh, right? That should make sense.
Yeah.
But in this case, we are talking about a wet adiabatic process. Now, adiabatic means no heat. So do we say this is no heat? This is zero. Well, if I move the parcel around adiabatically without heat, then there is no change in the potential temperature, which makes sense. But this is what adiabatic, so what heat is being used or released inside the parcel? It's the latent heat that's being released. Well, what determines the amount of latent heat that's being released is going to be the amount of the capacity change
Determined by, of course,
times the latent heat of vaporization, and that's going to be dq. Now, why do they put a minus sign in here?
Because it's a loss. You're taking heat, you're taking,
If the capacity goes down, then dW sub s is negative. But a negative
is a positive.
positive, which means I'm condensing water, which is releasing heat. So heat goes up. Can you follow that reasoning? Do you guys understand what I'm saying?
Okay.
Yeah.
Yeah.
What, in a wet adiabatic parcel, as I lift that parcel, do you agree the temperature is getting colder and the capacity is decreasing?
Mhm.
Well, the capacity decreasing means that the value of dW sub S is negative. What's the change in the capacity? Negative. But a negative times a negative is a positive heating term. Water vapor condenses, latent heat is being made real. Means the heat is going up. So given that, I now substitute into this equation what dq is. And I get LV, oops, let's use a pen, LV over CP over, which way do I want to put it? Over T times dW sub S, the change in the capacity, is equal to how the potential temperature changes. With the minus sign. So the only thing I did additional was divide both sides through by CP. Okay, so if you want, you could go like this, and you could put it there. Put it over there. Fair enough? Now, do you understand that in the parcel, and I just want to kind of come up with an idea. Do you agree that the air, when we're talking about a wet adiabatic process, the air is saturated?
Mm-hmm.
Which means the relative humidity is 100%, which means W and W sub S, W is equal to W sub S. So the amount of vapor that's actually condensing is the amount of vapor that has to condense in terms of W sub S. So when we say delta W is releasing the heat, that's true, but that's the same thing as delta W sub S because they're the same with the air saturated.
And if I'm right, if we're ever talking about the wet adiabatic collapse rate, it has to be saturated, right?
If it's not saturated, you're talking about the dry adiabatic collapse rate, which we already calculated.
All right.
So this only works. That's why we can use W sub S rather than W. Okay, now where are we? We're at 316. We're at 368. Okay, so I'm going to do this. I'm going to erase all of this. And I'm going to go to minus LV over CP T dW sub S is equal to d theta over theta. Now, do you agree that what we're trying to say is, and this should make some sense to you logically. So watch the screen and tell me if this makes sense to you. When the capacity is changing when the air is saturated, water vapor must be condensing. The amount of latent heat that is released and the specific heat of air at constant pressure at a temperature, so the temperature matters. How much heat goes into that will cause a change in theta at a theta. You're dividing it by theta, but that's really what the change in theta is at a potential temperature. So these things, do you agree that to some extent this relates to that? The difference is what's the pressure? So all you're saying is that the heat that's going to be released, given the latent heat of vaporization and the specific heat, is going to cause a change in the potential temperature, right? So what we say is, and if you remember this from severe, if I lift a parcel and water vapor is condensing, theta starts going up, right? Because you're heating the air. Theta goes up to what point? Until all the vapor is gone, and then when all vapor has condensed, what do we know? Theta becomes what? Theta E. Okay?
All right. So for purposes of just the math behind it, theta E is theta just after all the latent heat is gone.
Right. Theta is now theta E when all the heat is gone. Yes. So theta keeps increasing until all the heat's gone. Now there's no more water vapor to condense out. At what temperature will that happen, technically? Right, 0 Kelvin. Because then there's no vapor. So here's the thing. You could say to yourself, well, gosh, what do we do when I've got derivatives on both sides of an equation? What do you think I should do, Jim?
Integrate.
Integrate. Oops.
Love that.
So I can integrate. And I will integrate over here. Can I just bring this out front? Is LV a constant? Say yes.
Yes.
Is CP a constant? Say yes.
Yes.
Yeah.
Is temperature a constant?
Definitely.
Yep.
Yes.
Why would the temperature be constant? I'm moving a parcel around. Is that temperature constant?
It's adiabatic.
And isn't there a relationship between, no, theta is constant. But isn't there a relationship between temperature and capacity?
Oh, I'm thinking if okay, no.
This is not a constant. Temperature is not a constant. So do I know how to integrate the left-hand side? You could say, well, I can do this. That's fine. I can even do this. But then I get the integration of dW sub S over T. And then I look at this and I say, wait a second. Can I integrate that?
No.
And the answer is, I don't know how to. That's
Yeah.
not
Doable.
So with dW sub S over W sub S, that's easy, right? But I don't know the relationship between these two things. I don't know what that is. So I cannot integrate it. So now it says from exercise 3.52, we show that, and then they do something. So now we go to exercise 3.52 in the back of the chapter. So we are now page 106. Does 3.52 look like it's going to be a really simple problem?
Now, what page is this? Back of the book or back of the chapter?
Page
107.
107.
All right. Yep.
So your assignment is to do this problem. Now they give you a solution. So your job is to figure this out. Do you think this is really simple? Do you think this is going to take you 5 minutes to work through it?
No.
I don't think so. It's going to take you a little bit of thinking. So I want you to do this problem, and I want you to turn it in. I'm going to set up a place for you to turn this in on the assignment sheet. Oops. Because I want to see what kind of work you do. Now, do you have to be right by this? No. Do you have to be perfect? No. Do you have to work through it as best you can? Yes.
So it's due by Thursday. Well, of course it's due by
Yep.
Thursday.
Assessment, assignment, problem 3.52. And I will just say it's due by, then when does it have to be due by? You're not going to do anything Thursday morning. Nobody gets up there. Jacob, you don't get up Thursday morning and work on intermediate before class, do you? Does anybody?
I did it today.
Two.
Well, let's make this by midnight. I just want to see your scores because I can give you any grade I want to. Depends on how I feel about you.
Problem 3.52. Sometimes I love math assignments for that reason. You just see like, do page, 17, this number through this number, and you get all these things, and then you just have the do this one problem.
Yeah. Well,
Like, oh
okay,
no.
so the idea is, and then once we get there, once we get to 369, once we do this problem, then the rest of it comes pretty quick. Like we'll be able to finish the theta e derivation, but this is the situation. Do you understand why we're doing this situation? Did I stop sharing?
No, you're recording.
No,
You
did I
stopped
stop
sharing,
sharing?
yeah.
That's sharing though.
So the reason we can't do this is because I need to be able to derive that, the change in capacity and temperature, because we know that there's a relationship. So we need to make that assumption. Once we make that assumption and say that this is true, then we can solve the problem easier. So your job is to do 3.52 because it says in the book, and for those of you who are students to become meteorology majors, in exercise 3.52, we show that, which means you need to do that problem. That's just the way things go. Okay, and that will be the end of class today.
All right.
Any questions?
Last two sessions have been a lot more confidence inspiring than the first two.
Oh, I love this, and I'm looking forward to, if you look at the next thing, we have static stability, so that you'll understand what that is, and then we do the second law, and we do engines, and I'm telling you, there's some really cool stuff in here. And so we've got a couple more weeks of thermodynamics, and then we'll move on to dynamics, which is totally different and totally way cool also. This is maybe one of my favorite courses to teach. It was certainly the hardest to get to a point where I could teach it well. I used to have to follow notes really carefully. And now I'm adequate at doing without it. So, okay, guys, I'll see some of you at forecasting. The rest of you I'll see Thursday.
Thanks.
See you on Thursday.
Bye-bye.
See ya.
See you Thursday.